equations of motion. So far, we have learnt and used the quantities associated with motion of an object, such as time, displacement, velocity, and acceleration. We shall now derive equations known as the equations of motion, or kinematic equations. The derivation of the equations of motion is not examinable, but helps in developing a deeper understanding of the equation. The application of the equations of motion is examinable. We shall only consider the case when acceleration is uniform, that is, constant. We know that the acceleration of a body in uniformly accelerated motion is given by A equals delta v over delta t, equals v final minus v initial all over delta t. Rearranging the terms, we get v final equals v initial plus a delta t. This is the first equation. Let us draw the velocity versus time graph of an object in uniformly accelerated motion. We see that the object has a uniform acceleration, given by the constant gradient of the velocity versus time graph. The initial velocity is v initial, and the final velocity is v final. The displacement can be known by finding the area between the graph and the horizontal axis. The area can be split as the area of a triangle and the area of a rectangle. The area of the rectangle is the length times breadth. The area of the triangle is 1/2 the base times height. From the definition of acceleration, we get v final minus v initial equals a delta t. Substituting in the area, we get area of triangle equals half a delta t times delta t equals half times a times delta t the whole square. We get the total displacement by adding the two areas. Delta x equals v initial times delta t plus half a times delta t the whole square. This is the second equation. If we make delta t the subject of the formula in acceleration, delta t equals v final minus v initial all over a. Substituting this in the expression for displacement, we get delta x equals v initial times v final minus v initial all over a plus half a times v final minus v initial the whole square over a square. Simplifying, we get therefore v final square equals v initial square plus 2a times delta x. This is the third equation. The average velocity for the time duration delta t is given by v bar equals v initial plus v final all over 2. Therefore, the displacement can be given by average velocity times the time. Delta x equals v initial plus v final all over 2 times delta t. This is the fourth equation. These four equations can be used for any time interval, even though we have derived the equations using the start and the end as the initial and the final instance of time.
Starting to feel it? Now go master it with Maski.